Hello everyone, I warmly welcome you to CR Digital Classes. In this lecture, we are going to discussing about one of the important theorem based on the general linear group of 2 by 2 matrices over real numbers. Okay, let's see the statement of the theorem. Show that the set GL of 2 comma capital R is defined as matrix ABCD, okay, where the elements are entries A comma B comma C comma D R belongs to real numbers and their determinant AD minus BC. Their determinant AD minus BC not is equal to 0. This set forms a group but not an abelian group under the matrix multiplication. Okay, so before going to start the proof, we have to discuss the definition of the what is the general linear group of 2 by 2 matrices. Okay, so you can see the proof, and first see the just overall definition. Let I am taking capital A is equal to ABCD is a 2 by 2 matrix, okay, where all entries belongs to real numbers. A comma B comma C comma D belongs to real numbers. Now det of capital A, that means determinant of capital A is, you can write AD minus BC, okay, AD minus BC not is equal to 0. Not is equal to 0 means it can be equal to 1, equal to 2, minus 1, minus 2, whatever the any integer value except to 0. Okay, if you take any 2 by 2 matrix, the det of that matrix not is equal to 0, then the set of the group of matrices formed by those type of matrices is called general linear group of 2 by 2 matrices over the real numbers. Now in this problem, in this theorem, we are going to discussing about this. We are going to show that it is a group but not an abelian group under the matrix multiplication. Okay, so let's start the proof. Given that simply the general linear group we are denoting in this format GL 2 comma R, where 2 represents the order of the matrix 2 by 2 order and the capital R represents the real numbers is equal to matrix ABCD, okay, where elements are entries belongs to real numbers and det AD minus BC not equal to 0. This is the set given in the condition. Now by using this definition we have to prove it is a group or not a abelian group. So first see it is a first we are going to prove that this GL 2 comma R, okay, is a group. Okay, so GL 2 comma R is a group. So now in that purpose only, first of all I am taking as closure condition. For any theorem or any property, if they ask to prove a group or a non-abelian group, you have to start the proof in this format only: closure property, associative, identity, inverse and commutative. So first of all, closure is nothing but here this problem we are going to prove on the matrix. So that's why let capital A comma B belongs to GL of 2 comma R, general linear group. Okay, now their multiplication A into B also belongs to GL of 2 comma R. Okay, so that means why? Because here A is a 2 by 2 matrix and B is a 2 by 2 matrix. Okay, so and det of A not is equal to 0 and det of B not is equal to 0. So therefore if you take their product A into B also, then you will get one 2 by 2 matrix only. For example, okay, I am taking capital A is equal to A1, B1, C1, D1 and capital B is equal to A2, B2, C2, D2. These are the two 2 by 2 matrices. Now A into B you can write as A1, this row, these two columns. You know very well matrix multiplication. A1, A2 plus B1 C2. Next A1 B2 plus B1 D2. Now this row and these two columns. So C1 A2 plus D1 C2, C1 B2 plus D1 D2. First we took capital A and capital B are the 2 by 2 matrices, okay, and their multiplication is also we got one 2 by 2 matrix. So therefore this resultant matrix also belongs to general linear group of 2 comma R. Clearly we can say that therefore general linear group of 2 comma R is closure, is closure. Now the second condition is associative condition. The second condition is associative. In this associative also we are going to take three matrices, okay, A, B, C, okay. So let A, B, C belongs to GL of 2 comma R. Then what is the condition? A into B into C is equal to A into B into C. As we proved in the closure property, the multiplication of any two matrices again is a matrix. The same logic here also using, okay. By trivially we can say that GL of 2 comma R is associative, no need to prove the proof, okay. So next third one is the identity. Third one is the identity. For identity, so let I am taking capital A. Capital A is equal to A1 B1 C1 D1 is the matrix belongs to GL of 2 comma R. Now according to the identity property, what is the condition? A into I is equal to I into A is equal to A. This is the condition. Now we have to substitute one matrix, okay, in place of capital I to get the its original matrix. That means here you have capital A into I is equal to A. This is the LHS condition. So now what is that matrix? What is the value of that capital I? You can easily imagine that capital I is 1001, okay, is the identity matrix, is the identity matrix. You can also cross check by doing the process, okay. So A into I is equal to, what is the A1 B1 C1 D1 into I 1001. So therefore if you do the multiplication process, this row, these two columns, okay. So A1 into 1 plus B1 into 0. Next to A1 into 0 అంటే 0 plus B1 into 1 B1. Next to C1 into 1 plus D1 into 0 0. Next C1 into 0 plus D1 into 1. So in this format again you will get A1 B1 C1 D1. Okay, again it is equal to A into I is equal to A. Then this I is called identity matrix. So next we have inverse condition. Fourth condition is inverse. In this condition, by using the identity matrix, we are going to find out the inverse matrix. So let capital A is equal to A1 B1 C1 D1 is the given matrix, okay, belongs to GL 2 comma R. There exists capital I is equal to 1001 is the identity matrix, okay, that is also belongs to GL 2 comma R. Now then A into A inverse is equal to capital I is equal to A inverse into capital A. This is the inverse condition with respect to matrix multiplication. Now take that LHS condition, okay. So before going to prove that LHS condition, first of all I am writing that formula for A inverse. You know very well, for the 2 by 2 matrices, A inverse is equal to adjoint A, okay, adjoint A by det of A, adjoint A by det of A. What is that adjoint A? Okay, So adjoint A is equal to, okay, so D minus B minus C A. Okay, so this is the formula for the adjoint A. Why? Because where A is equal to A, B, C, D. Sorry, A1, B1, C1, D1. Then adjoint A is equal to D1, B1, C1, A1. Now and det A, det of A. Det of A is nothing but A1 D1 minus B1 C1. This det value is always not equal to 0. So now substitute these values in A inverse. So therefore A inverse is equal to 1 by A1 D1 minus B1 C1 into, what is the adjoint A value? D1 minus B1 C1 minus A1 plus A1. Okay. So therefore we can write A inverse is equal to, clearly we can write D1 minus B1, okay, so minus C1 A1 by A1 D1 minus B1 C1. So clearly A inverse is equal to D by A1 D1 minus B1 C1 minus B1 by, okay, so A1 D1 minus B1 C1 minus C1 by A1 D1 minus B1 C1 minus A1 by plus A1 by A1 D1 minus B1 C1. This is the inverse matrix of capital A. Okay, for A is equal to A1 B1 C1 D1. Okay, so in this format we got identity element is equal to 1001 and inverse A inverse is equal to this above matrix. So clearly we can say that this, the set of GL 2 comma R is a group, is a group. Now the next condition is, what is asking, show that it is a non-abelian group. Non-abelian group means not an abelian group. To prove that condition we have to take commutative property. We have to take commutative property. Commutative property. Okay, so let A and B belongs to any two matrices in the GL of 2 comma R, okay, with det of A not is equal to 0 and det of B not is equal to 0. Then their product det of A into B is equal to det of A into det of B. Okay, now I am taking it as condition. So for capital A comma capital B belongs to GL of 2 comma R. With respect to matrix multiplication, what is the commutative property? A into B is equal to B into A. Okay, this is the original property. But in the matrix, if you take any two matrices, their multiplication will never become equal. Okay, so clearly we can say that A into B is not equal to B into A according to the matrix properties. We can also prove. So therefore, commutative property does not exist in the general linear group. That's why we are calling it as general linear group of 2 by 2 matrices over real numbers is not satisfying abelian group property. Okay, so abelian group property. So therefore finally we can give the conclude is that, okay, general linear group of 2 by 2 matrices over real numbers is a group, not an abelian group, not an abelian group, not an abelian group. This is the explanation. Thank you.